very much. It's my honor and pleasure to be talking to you today about the likelihood correspondence. So let's just jump right in. So yesterday, Seth told us about multivariate Gaussian random variables. Yeah, they had a very complicated density function. And if you were frightened by this, you don't need to worry. So today we talk about discrete random variables. So what is a discrete statistical model? A discrete statistical model is a subset of the probability simplex. So the probability simplex in the m-1 dimensional simplex is just the points in the real positive orthant such that they sum up to 1. So we can think of a point in our model as representing a probability distribution. Yeah, so every coordinate is positive, and the summing up to 1 makes them a probability distribution. So far, so good. And now, if M is semi-algebraic, we win, and we are in the realm of algebraic statistics. Now, often in algebraic statistics, we represent a statistical model by a projective variety X. Now, this variety lives in a projective space of dimension m-1. And then we somehow need to make sense how to pass from here to the probability simplex. So we also need to specify some sort of map that brings us from projective space to, let's say, complex space, so that in the end, we can apply our map and then intersect again with the probability simplex. Okay. So in this case, if we just describe this projective variety, then we have an implicit model description.
Well, you don't need a map. There's the simplex is the positive part of the objective. There's no map needed.
Yeah, but I will have different views on how to interpret this. So I want to specify this map because I want to switch perspective. Okay, so here's a simple example. So I take two binary random variables, y1 and y2. And then I have a joint probability distribution, Pij. So now y1 and y2 have states 0 and 1 each. So I get states P00, P01, P10, P11. And then I can write down this variety, right, which is cut out by the single equation. And I claim that this is the independence model. Now, why is this the case? Well, we all know, or at least we learned yesterday in the talk, that being independent means that this probability distribution factors. So all of these Pij factor into Pi1 times Pj2, which means that if I write down a matrix P00, P01, P10, P11, this has rank 1, so its determinant vanishes. Okay, yeah, and then in this case, I just mod out by the sum of the coordinates, and this is very simple.
Okay, the map is not well defined as a rational map.
That's true. So now, so here in this example, this variety was given implicitly. In this talk, I want to focus on parameterized discrete statistical models. So I will fix throughout the talk, I will fix m homogeneous polynomials, f1 through fm, in n variables, and I denote this polynomial ring by R. And they are of degree d1 up to dm. And I have this slightly technical assumption that m is larger than n. So this makes the complement of the union of all these hypersurfaces a very affine variety. But yeah, you maybe don't need to worry about this too much. Okay, so I might have already given it away. So we think of the collection of these Fi as a hypersurface arrangement in projective space. Okay? By abuse of notation, sometimes I will refer by A, I mean either the collection of polynomials, or I mean the geometric collection of hypersurfaces. Now, how do I interpret this as a discrete statistical model? So now, if I take Fi of the same degree, And now I only consider the first m-1 polynomials, and then I set the last polynomial to be equal to the sum of all the previous ones. Then I have this map to projective space, which says takes an x and evaluates it at all these polynomials. And then the image closure gives us a discrete statistical model, and I restrict to this chart where the last coordinate is 1. Then I obtain coordinates. I have fi over the sum of all these. And now this can be interpreted as the probability of observing the ith state. And here's a shameless advertisement now where we work in this setup. So as of this morning, there's a new preprint on the archive with Hannah Friedman and Bernd. And there we consider the setup where all these fi's are squares of linear forms. And then the last polynomial is the sum of these squares. So yeah, please do check out this preprint. It's called Squared Linear Models. Okay, so you can think of these xi's as being the parameters of the model. And now there's a classical question in statistical inference, which is given a statistical model, M, and a data point, what is the probability distribution in the model that best explains this data? So what is data? Well, most of the times in statistics, it's just a count of certain event outcomes. Okay. So maybe I want to make a probability distribution describing the people in this room, right? And then maybe one event might be there are female mathematicians wearing glasses, and then I just count how many there are, right? 1, 2, and so on. Okay, so in this case, my data is just a tuple of natural numbers. And yeah, so I might be interested in the probability distribution in this model. I can also ask the question, what are then the parameters that give me this probability distribution? And this is a slightly different question. I mean, if my parameterization is, I don't know, 4 to 1, then for each p hat, I get 4 sets of parameters, but it might also have infinite fibers. And yeah, this whole process, how to get from a data point and a model to this probability distribution p hat, this is called maximum likelihood estimation. Why is it called like this? Well, we have a likelihood function. So if we fix such a tuple of data, then we can set up the likelihood function. The likelihood function is we take all these polynomials fi that we fixed before, we raise them to the si power and multiply them. Okay, and yeah, the name already suggests we want to maximize this likelihood function. And instead of maximizing the likelihood function, we can also just take the logarithm of this function and maximize this log likelihood. Okay, so the log likelihood is simply you take the logarithm of this f to the s. And then the goal of maximum likelihood estimation is to maximize this log likelihood function. So here's a very simple example. So I just take some more, I take some linear forms here. The first 4 I've just chosen. And then the 5th one is the sum of the previous ones. And I've just chosen this data point here, 1, 2, 3, 4. And then in order to make this model work, I need to set the last data coordinate to be minus the sum of the previous ones. So this makes my likelihood function then well defined. And how do I solve this? Well, when I want to be cool, I use numerical algebraic geometry. And so this is some code. Now, I realized it might be a bit dangerous to present this code in front of such an audience. So Paul, you can tell me later offline how to do this in 1 line. But so I do this, right? And then in the end, I obtain that this is my MLE. So up to scalar, right? So this we work projectively. So this is defined up to scalar. I get this result. And what do I do basically here? Well, I guess the key step is I differentiate the likelihood function, and then I solve the system in the end. So in order to maximize the likelihood function, we want to look at the critical points of it. And this brings us to the definition of the likelihood correspondence. So we take the set of parameters and data points. So we think of them now as living in Cn and C to the m. And we take all such pairs of parameters and data such that for this particular data, x is a critical point of the log likelihood function. Okay. And note that these are rational functions. Right? So it makes sense to, in the end, take the Zariski closure of this in projective space. And then I have these two slightly more technical requirements. So the first one is that the likelihood function should not vanish. And this is to make the logarithms well defined. Otherwise, the log likelihood function is not defined. And then the second assumption is that my parameters should give me a smooth point in my model. Okay, and this is to make the number of solutions to be constant. So if I'm on a singular point in my model, I can have additional solutions to my likelihood equations that I don't want to consider here. Okay, and then I take the Zariski closure of this set inside this product of projective spaces. So one is the parameter locus and one is the data locus. Okay, so the likelihood correspondence completely describes the dependence between data and critical points of my log likelihood function. Yeah, capital F is this parameterization map that I've written down before. So this was, you take an x and you evaluate it at all the polynomials fi. And yeah, it's not too hard to show that this variety is irreducible of codimension n. Okay? So n, remember, n is the number of variables, and it's always codimension n. And the prime ideal is what I denote by I of a, and this is the likelihood ideal. Okay? And the goal of this talk basically is to describe this likelihood ideal so that we have a complete description of our likelihood correspondence. And in fact, if you only look at the parameter locus inside Cn, such that you have smooth points, then LA is a vector bundle over this parameter locus. So globally, LA is not a vector bundle. Yeah? So if you take this closure, it's not a vector bundle anymore. Yeah, here it's just an affine vector bundle in this case. Yeah. So now I've talked a lot about statistics, but maybe you don't like statistics. Well, in this case, the likelihood correspondence can still be interesting for you. And that's because maybe you like particle physics. And then, and then it turns out that the same object appears in particle physics under the name scattering correspondence. Okay, so in the business of computing scattering amplitudes and canonical forms, people write down so-called scattering equations. And the scattering equations are exactly the critical equations for the log likelihood function. And then they define an object called the scattering correspondence. Okay, and you can read about this in this survey paper by Thomas Lamb. So yeah, even if you don't like statistics, maybe this is still an interesting object for you. If you do like statistics, then I have another application for you, what to do with the likelihood correspondence. And the application is log Voronoi cells. Okay, so what is this? So you fix the probability distribution P inside your model. And now you kind of ask a reverse question to maximum likelihood estimation. And the question is, now what is the set of data points? And now, okay, previously I've taken my data just as tuples of natural numbers, but I can rescale all the data so that it lands inside the simplex. So I might call this the data simplex and not the probability simplex anymore. So what is the set of data points such that P is the MLE for this particular data? Okay. So in other words, P should be the global maximizer of the log likelihood function for this particular data S. And I'm looking for the locus inside the probability simplex where this happens. Okay, now if my P at least is generic enough, then the fiber of the likelihood correspondence over P gives me a linear space in data space. Right? This is what we discussed before. It's an affine bundle. So this is just a linear space in data space, and I can intersect it with this data simplex. And the result is a polytope that's called the log normal polytope. So what's the interpretation of this log normal polytope? Well, it means that for any data point you pick here, and then you look at the log likelihood function for this particular data, then P will be among the critical points of the log likelihood function. Okay. So it is one of the critical points, but it might not be the global maximizer. Okay. So there is a convex subset inside the log normal polytope such that P is actually the maximizer of the log likelihood function. And this convex subset is called the log Voronoi cell. So I think this is a very interesting object for statisticians because it tells you how much you can perturb your data so that you still get the same MLE. And here's now two pictures from our recent work on squared linear models, which depict these log Voronoi cells. So here I've chosen as my linear forms a very simple example, x1, x2, and x1 plus x2. So now I take the squares of these, and these define my FIs. And then it turns out the model is just a square inside this probability simplex. So now I've identified the probability simplex with a data simplex. It's two-dimensional. It's a circle, sorry. Did I say square? Oh, yeah. It's a circle. I squared the circle, yeah, sorry. It's a circle, yes. And then these dashed lines here, these are precisely the fibers of my likelihood correspondence. Okay. Yeah, they would continue forever, of course, but for simplicity of the picture, I've cut them off here. And now the log Voronoi cell turns out to be just this piece of this fiber, which is inside this chamber that's marked in red. Okay. So for this particular P, you look at the fiber of the likelihood correspondence. So this is this whole line here. And then if you restrict it to this chamber, then you get the log Voronoi cell. And so this is a very simple example because now this log normal polytope is just one-dimensional. Here's a slightly more complicated example. So this is already the log normal polytope for a certain point in this model. And the log Voronoi cell is this shaded area in here. So what are these other regions? Well, it turns out that for these squared linear models, the situation is very nice. And all critical points correspond to one particular region of the hyperplane arrangement defined by these linear equations. Okay. And now you can ask, okay, for let's say I take a data point in here, what region does the MLE correspond to? And the tiles in this log normal polytope correspond to the regions that the MLE lies in. And yeah, this particular tile here is now the log Voronoi cell. So this might give you the impression that all of these log Voronoi cells are polytopes. That is in fact not the case. So if you take a generic model of this type, then you will not see a polytope as your log Voronoi cell. Yes. So in fact, the boundaries can look very wild, and probably they will also be non-algebraic, though we don't know this. All right. So hopefully you're now convinced that the likelihood correspondence is a very nice object. And the question is, of course, now how to compute this likelihood ideal. So if I localize my polynomial ring at all these polynomials fi, then the likelihood ideal is very easy to describe because you can just write down the critical equations. So this is precisely, you apply a partial derivative to the log likelihood function, and then you get these rational functions here. Now inverting these fi's is allowed, so this generates the likelihood ideal inside this localized ring. But of course, we are not only interested in the description inside this local ring, but we want the description inside the polynomial. So now I can, of course, just clear the denominators, but this will introduce extra solutions, right? This will introduce solutions where the fi's vanish, but I've excluded them from my likelihood correspondence. So what can I do? Well, I can saturate along these fi's and along the singular locus, right? Because this was the definition of the likelihood correspondence. I cut out this locus by doing the saturation. So this is what's been proposed in the early days of likelihood geometry. But of course, if you've ever computed a saturation in Macaulay 2 or any other computer algebra package of your choice, you know that this is a very expensive step to do computationally. Okay. So in many instances, this will not terminate for you in a reasonable time or in your lifespan. Okay, so what else can we do? So now I'm going to introduce an object called the likelihood module. And first I look at this matrix Q. So what is this matrix Q? Well, it consists of two blocks. On the left-hand side, I have this diagonal block with the fi's on the diagonal. On the right-hand side, I have a Jacobian of these fi's. Okay, so this is an m by m plus n matrix. And now if I take an element in the kernel of this matrix, I can write it as A, B, where A corresponds to this first block and B corresponds to the second block. Okay. And now I take a whole generating set of this kernel Q. I write it in this way, and then I put all the columns next to each other, and I obtain two matrices, A and B. And the co-kernel of this matrix A is what we call the likelihood module. So at first, this definition might seem a bit obscure. It is, in fact, related to the theory of A derivations. So if you know, for example, hyperplane arrangements, you have logarithmic differentials, and dually, you have A derivations. And it turns out that the image of this B matrix is isomorphic to the module of A derivations. So this is how we found this likelihood module. But if you don't know about these derivations, don't worry. So now I'd like to introduce the Ries and symmetric algebra of a module. Well, the symmetric algebra is pretty easy. So if you have any module that's a co-kernel of a matrix, then the symmetric algebra just turns this module into an algebra. So you want basically the same relations to hold. So what do? You append m many extra variables. And this might also already be a bit suggestive here that I've written these SIs. And then here, what is this ideal? Well, I have a row vector of SIs, and I multiply it with my matrix A. And then I get, again, a row vector with linear entries in the SIs. And I take each entry here, and these are the generators of my ideal. And because this ideal will appear many times, I call this the pre-likelihood ideal. Now, the Ries algebra is probably known to many of you, at least in the case of an ideal, because it's just a blow-up algebra. So if you have a closed subvariety of projective space, which is defined by I, and you want to blow up along I, then you build this Ries algebra, and then you take proj of it, and then this will be the coordinate ring of the blow up. what is the Ries algebra of a module? Well, you can define the Ries algebra of a module for any module over any ring. But then you need a bit more complicated and less constructive method. But if R is a domain, this construction is not too difficult. You just take the symmetric algebra of the module and you mod out the torsion part. In particular, this means that the ideal that presents the Ries algebra contains the pre-likelihood ideal. Okay. And now there is this proposition by Eisenbud that tells you how to obtain the ideal presenting the Ries algebra. Namely, this Ries ideal is given by a saturation again, and it's a saturation of this I0. And you need to find some element P such that if you invert P, then M becomes a free module over R. Such an element always exists. And then you can perform the saturation step. So you're only a saturation away from the pre-likelihood ideal to the likelihood ideal. And yeah, this proposition then was used in this theorem. So this was a theorem by Thomas Kahle, Lukas Kühne, Leonie Mühlherr, Bernd, and me. And it says that the Ries algebra of the likelihood module is the quotient of this coordinate ring by the likelihood ideal. Or in other words, likelihood ideal is equal to the Ries ideal of the likelihood module. So this gives a new way of computing this likelihood ideal. One case is very nice, which is that if this pre-likelihood ideal is already prime, then the saturation step is unnecessary because it doesn't do anything. So in this case, we already know that the pre-likelihood ideal must be equal to the likelihood ideal. So no saturation in this case is necessary, and the computation is very efficient. And because this case is so nice, we call arrangements with this property gentle. Okay. So a gentle arrangement is an arrangement such that the pre-likelihood ideal is prime. So here's an example, or more of a non-example. So I take the independence model, but now I represent it in a slightly different way as before. So I take three variables, x1, x2, x3. And for example, I can think of this as I have two biased coins. x1 is the probability of my first coin to give heads. x2 is the probability of my second coin to give heads. And then I write down all the probabilities for the outcomes. Then I get x1 times x2. Now I would have 1 minus x1 times x2, but I need to homogenize it. So I introduce this variable x3. And in the end, I need to put this homogenizing variable x3. So this is how I derive this model. Now, this is a free arrangement. And this means that the module of derivations, of A derivations, is a free module. So if you know hyperplane theory, then you know that this is a very interesting property for people studying hyperplane arrangements. And there is this Terrao conjecture which tells you, or which states, that the freeness of an arrangement is a combinatorial property that can be read off from the matroid of the hyperplane arrangement entirely. And this is a very difficult conjecture. It's still open, and this has kind of driven the field a long way. So this is a free arrangement. So it has this very nice, very special property of being free. However, it is not gentle. Okay. So I can compute the pre-likelihood ideal, and I do a primary decomposition, and I have these two prime ideals. The one on the right-hand side is my likelihood ideal, but I have this additional prime ideal here. So now I also see that if I take the pre-likelihood ideal and I saturate at x3, I get the likelihood ideal. Okay. So it's not necessary to saturate at the product of the FIs as we've seen on a slide earlier. It's just necessary to saturate at x3 here. And I think it's kind of an open and interesting problem to determine the the minimal saturation that is needed in this non-gentle case, how to pass from the pre-likelihood ideal to the likelihood ideal. And there is another theorem that I kind of like. So under the assumption that I have a gentle arrangement, then the likelihood ideal is a complete intersection if and only if the arrangement is free. Okay. So this is really a necessary assumption, as we can see in the example above. So here n is equal to 3, and I told you the likelihood correspondence always has codimension n. So it has codimension 3, but here these are minimal generators, and I have 4 of them. Okay. So this assumption is really necessary, but if I have a gentle arrangement, then I get a complete intersection if and only if the arrangement is free. Okay, here's a different description of the independence model. And I introduce variables A0, A1, B0, B1. And I can write down the probability distribution as this. And now what is my model? So now I take these 4 variables, and the arrangement just consists of taking these 4 variables together with another polynomial, which is the sum of these probabilities. Okay. And I call this the toric description. And this is because, well, these parameters here, they give a monomial parameterization. So these give rise to a toric variety representing the independence model. And then if you exclude from this toric variety, you exclude the hyperplanes, the coordinate hyperplanes together with the sum of the coordinates, then this will give an isomorphism of very affine varieties to just this polynomial here being non-vanishing. Okay. So in the end, it turns out that the likelihood functions for this model gives you exactly the likelihood function of this toric model of the independence model. So it turns out now that in this case, we do have a gentle arrangement. So the likelihood ideal is equal to the pre-likelihood ideal. This is a gentle arrangement. So gentleness really depends on the parameterization that you choose. So it's not invariant of the model. It depends on the parameterization. What's also very nice is now, so this likelihood correspondence lives in this product of projective spaces. So you have a bi-degree, and this bi-degree is a homogeneous polynomial of degree codimension, which is 4 in this case. And from this multi-degree, you can, for example, read off the maximum likelihood degree. So the maximum likelihood degree is the number of critical points of the log likelihood function for a generic data point. This already appeared yesterday a couple of times. And in this case, it's the leading coefficient of the multi-degree, and leading here in the tau variables, as I've written down here. Okay, so the leading coefficient is just 1, which is the ML degree of the arrangement. And in this case, it's also the ML degree of the model because my parameterization is nice. And I'd like to mention this result by Juniha that the ML degree, that the ML degree is equal to the signed Euler characteristic of the hypersurface complement in projective space. Okay. So there is a topological interpretation of this maximum likelihood degree. Okay, so now I focus on certain very specific arrangements. And yeah, maybe as an algebraic geometer or as a commutative algebraist, the first question is, what happens for generic models? And it turns out that we have a very nice meaning of what it means to be generic in this case. And this genericity is captured by being strict normal crossing. Okay. So a hypersurface arrangement is strict normal crossing if all the intersections are smooth of the correct codimension. So in particular, this implies that all the hypersurfaces themselves are already smooth. So maybe a picture here is telling more than these 2 lines. So on the left-hand side, we see an arrangement that is not SNC. And why is this? Well, you take these 2 hyperplanes here, they intersect in this line, and now this line is tangent to this hypersurface. And this tangency violates the smoothness. But if you perturb this hypersurface here a little bit, then you do get an SNC arrangement on the right-hand side. Okay, so this already tells you that this is some kind of genericity, because this perturbing brings you into an SNC situation. So this is a geometric condition, what it means for the hypersurface arrangement to be generic. You can also formulate this in algebraic terms, in terms of discriminants. So you can write down discriminants for all of these polynomials and their intersections to be smooth of the correct codimension. So this brings you into, gives you a product of so-called mixed discriminants. Oh, there's a question. Yeah, okay, the question was, is there a distinction between normal crossing and strict normal crossing? And yeah, there are various notions that are very similar around in the literature, and some of them require the hypersurfaces to be smooth, some of them don't. Sometimes you allow nodal singularities. So I think so I would understand if I take a normal crossing arrangement, I think I would allow things like this would be a normal crossing arrangement, but it's not strict normal crossing. Okay, so locally here, this looks like a normal crossing, but it's not strict normal crossing because it's singular. So this would be my understanding of difference between normal crossing and strict normal crossing. Yeah.
You also don't insist that your intersections are connected?
No. I mean, this is not connected with. Sorry.
Well, I guess in your definition, in each strata, the different functions would be local coordinates.
That's right.
And that's what's different about it. No case.
That's right. That's right.
For keys, they're just happy. Grab them on the pad. Yeah, exactly.
Yes.
Yeah.
Okay.
Yeah.
All right. So you can also define this algebraically in terms of discriminant. You can also define it topologically, it turns out. So this means that generically you do get the correct Euler characteristic, or the other way around. If you don't get the correct Euler characteristic of the arrangement complement, you are not SNC. And in this situation, in a paper with Thomas Kahle, Hell, and Bernd, we figured out that if you have a strict normal crossing arrangement, then it's very nice to write down minimal generators of the likelihood ideal. And these arise as maximum minors of this funny matrix here. So what is this? You might remember this matrix Q from earlier. So you take this matrix Q with this diagonal block on the left, the Jacobian block on the right. But now we remove the first column. So this is an arbitrary choice. We could have removed any of the first m columns. But yeah, we chose to remove the first one. And then we append another row in the end with s's here and zeros here. Okay. And it turns out the maximum minors of this matrix generate my likelihood ideal, together with another linear form that includes all the s variables. So if you know about derivations, then this linear form here is related to the Euler derivation, which always appears in the derivation module. Okay. So corollary, all SNC arrangements are gentle. A few words about the proof, because I think it's rather nice. So it turns out that under the SNC condition, the kernel of this has constant rank over projective space. And if you were here on Saturday, then you know how to compute the kernel of a matrix. And you know that under certain assumptions, namely if the Buchsbaum rim complex is exact, then the kernel is generated by the circuits of this matrix. And this gives you an inclusion of ideals. So here, this is now the ideal generated by the maximum minors of the matrix together with the linear form. It's included in the pre-likelihood ideal. And this is, on the other hand, included in the likelihood ideal. And then we use another nice complex from the appendix of Eisenbart, which is the Egan-Northcott resolution, which shows you then, which gives you a resolution of this ideal here, and shows you that this ideal is Cohen-Macaulay of the correct codimension. And then up to radicals, we get an equality here. But how do we resolve this up to radicals? Well, the idea is that we look at the multi-degrees of these ideals. Okay, so if the multi-degrees coincide, then we know that also the non-reduced structure must coincide. And we do this by applying this very classical formula from algebraic geometry, the Gambelli-Thom-Porteous formula. What is this? So we can consider the matrix QS without 1 as a map of vector bundles. So you just need to carefully assign degrees to the entries of this matrix, and you write it in terms of vector bundles over this product of projective spaces in this way. And then the formula gives you that the multi-degree can be read off as this double Schur polynomial in terms of this quotient of Chern classes of these vector bundles. Okay. And in this case, this formula is super easy because if you take a 1 here, then this is actually just one entry in a certain matrix that you need to construct. So this double Schur polynomial might sound scary if you don't know combinatorics, but it's actually, you write down a certain matrix, and this is one entry of this matrix.
That's the partition.
I think it's the all one partition.
All the way down.
Yeah, no.
So it's really just an element of the vector.
Yes, exactly.
Okay, so that's really not.
Yeah.
It's Chern class.
That's right.
Okay, so it's not.
So you just write down this quotient, and you need to pick the right degree.
It's Chern class.
Yes. Yes. But this is because this situation turns out to be very nice because we take the maximal minors, and this makes it very nice. If you had taken other minors, then you would actually need to compute this Schur polynomial. Okay, and then you do this computation, and you can also compute this directly. So this is the multi-degree for this generic arrangement. You can compute it directly via this generating function over here. So you take this simple generating function, you extract the Zi coefficient, and then this gives you the coefficients in the multi-degree. And then it turns out, the multi-degrees coincide. Okay, so now suppose one of the hypersurfaces now has an isolated singularity. And I would also like for assumption, for simplicity, to assume that it does not lie on the intersection with the other hypersurfaces. Sorry, there's a typo here. So every good talk needs a typo. So this means other hypersurfaces. So the conjecture would be that this is still gentle. So the pre-likelihood ideal is still equal to the likelihood ideal, but the inclusion of this ideal of maximal minors is now strict. So this nice characterization does not hold anymore. One way to see this is that the ML degree changes by the Milnor number of this isolated singularity. So if you remember this characterization of the ML degree as this Euler characteristic, then you might know that if you introduce this isolated singularity, this Euler characteristic will change by the Milnor number of this singularity. And the question we want to focus on in this project is, can we find a nice description of this likelihood ideal in the case that we have an isolated singularity? A quick look at the Betti table. So this is an example for 3 variables, 3 lines, and 1 cubic. In the generic case, so how to read this? So in this column, you find the generator. So you see this one linear form, and now I have 3 generators in degree 4. And here in the node, if I introduce a nodal cubic, I get 1 additional generator here. And the goal of the project is to explain these additional generators. Okay, thank you very much for your attention.